Chapter 6, Force and Motion, Part 2. Or, the way I like to put it is that it's just more force and motion. So Chapter 6 is really just a continuation of Chapter 5. They probably could have made them a single chapter, except for then it would be a super long chapter, so they split it off into two separate ones. So we'll take a look at some other forces and some other considerations we can take in the context of Newton's laws that we saw in Chapter 5. Before we get into some of those other forces and considerations, I wanted to highlight this problem-solving strategy for forces. So this should work for Chapter 5 or Chapter 6. First, you want to identify the objects of interest. So, what are we most interested in? What is moving? What has forces acting on it? 2, draw all the forces that are acting on each object. Usually you need contact, so you could draw a dotted line around the object, see what's touching it. Anything that's touching it will probably be a force. There are a few long-range forces, notably gravity is one of those, but otherwise it's mostly going to be contact forces. Then draw your free body diagram. So reduce the object down to a single point, copy the forces over from the drawing and show them as pulling on the object with the tail connected to that dot. Choose a coordinate system of x and y axes. Usually it's just going to be horizontal and vertical, or a classic coordinate system. But if it is an inclined plane, you'll usually rotate your axes to line up with the inclined plane. If any forces point in both the x and the y directions, you want to break them down into components, right? So if there's one that's some combination of x and y, you want to figure out how much of it is in the x direction, how much is in the y direction. Finally, identify any accelerations. Is it accelerating along the ramp? Is it stationary? Is it moving at constant velocity with no acceleration? These are all good considerations. Once we've gotten that free body diagram, we can use Newton's second law. It's going to be one of our favorite equations of the semester. F equals ma, specifically F net is equal to mass times acceleration in the x and the y directions for each free body diagram. Sometimes we won't need every direction, but it doesn't hurt and it doesn't take that long once you get in the habit of it. So I encourage you to just always do that, and then you have it done. F net is the sum of all the forces acting in that direction, added or subtracted from each other, depending on if it is moving in the positive direction versus the negative direction. M is the total mass considered by your FBD, and A is the acceleration of that object in one particular direction. So I'm sorry, there should be a sum in here. S-U-M. There we go. Once you've applied Newton's second law to each of the axes, each of the objects, you might find that you have multiple unknowns. Like our example with the sliding block and the hanging one, we didn't know tension nor acceleration. Well, we can eliminate one of those by first solving for it and then substituting it into the other equation. So we're pretty well established at this point. And so this gives you an overview of the process. This is a lot of details, so if this is too much words for you, you're welcome to back off of it, but I wanted to put it out there in case you do really like all those little details. This procedure should work for chapters 5 and 6. Really solid procedure. Anytime forces are involved, we're going to be following this procedure of choosing the objects we want to focus on, creating a free body diagram, using Newton's second law, and then plugging and chugging, and we'll be home free. So this introduces chapter 6, more to come.